Now let's demonstrate Elastic Net embedded feature selection algorithm with an example of predicting house prices application. So now let's do the feature selection in predicting house prices using Elastic Net. So here selecting relevant features like the number of bedrooms, square footage, and location to predict house prices. And that's what the example remains same. The data story remains same. Then the method only changes. So step one, load the data and import libraries. As usual, the dataset includes various variables such as the number of bedrooms, square footage, location, age of the house, bathrooms, garage capacity, overall condition, and actual house price. I'm just quickly running through it. Then data pre-processing. Here we will encode the location variable using one hot encoding or any suitable encoding technique. For that we'll be using get underscore dummies method. Then split the data into features capital X and the target variable small y. Then split the data into training and test sets. Basically, we will take test size of 20% and random state of 42. And then standardize the features. As usual, we'll use a standard scalar. We'll instantiate the standard scalar class object and we'll fit the data into that. We'll get the X train scaled and then X test scaled both for us. So that's what importing the libraries quickly. Pandas SPD, a scalar library, model underscore selection package, and train test split. Then a scalar library pre-processing package, one hot encoder. Then a scalar library linear underscore model package and elastic net module. Then a scalar library matrix package and mean squared error module, and these are the things we will be importing. Then load and pre-process the data. So use a read underscore csv function from the pandas library and give the directory or location path of the respective file, and we have given that, and then encoding the file with the get dummies, and then mentioning the column name, and finally first split capital X or feature and small y target variable, then split the data into training and testing sets, which is X underscore train, X underscore test, Y underscore train, Y underscore test. So we'll be using a train test split class object, and then capital X feature, small y target, and then test size is 20% and random state is equals to 42, and this is what the pre-cap of our project story. Now let's get into the main story. So next, the important step is to create the elastic net model, elastic net regression model. So create an instance of the elastic class, elastic net class, and specify the desired values for the hyperparameters alpha and L1 ratio, that is L1 ratio, L1 underscore ratio, which is beta. Okay, so that's what these are the two hyperparameters this elastic net consists of, whereas L1 lasso regression just alpha, ridge regression just beta, that's L2, whereas the elastic net model consists of two hyperparameters which are alpha and L1 ratio, which can be called as a beta. Okay, and let's instantiate the elastic net class object. For that I need to call up elastic net class, and inside that I have to give two arguments which are hyperparameters. I'm going to go with alpha value of 0.5 and beta value or L1 ratio of 0.5. Okay, next next step is to fit the elastic net model. The instantiating the elastic net class object was done. Now it's time to fit the elastic net model. So fit the elastic net model to the training data using the fit method. That's what we're gonna do. So elastic net is our the object that we have created. It's the elastic underscore net is the variable name that we have given for the elastic net object. So then I'm going to call up the fit method from the elastic underscore net object, and the arguments I'm going to give are x underscore train, y underscore train. Okay, that's what I have given. So with this, the fitting the elastic net model to the training data will be done. Now let's move ahead. So then after that, if you want to get it, you can get the important features, which is x dot columns, and then feature importances should not be the basically the coefficient should not be zero. And now it's time to look into the retrieve the coefficients. So retrieve the coefficient estimates from the fitted elastic regression model using the coefficient underscore attribute, and that's what we'll be doing. So we'll be getting the coefficient estimates directly from elastic net object, and you have to just call up the respective attribute without mentioning any parentheses. Okay, so then so what's next? The next step is to, once that's done, so evaluate the model's performance. Use the model to make predictions on the testing data using the predict method. Then evaluate the performance of the model using appropriate evaluation metrics such as mean squared error or R squared. So here we'll be using the mean squared error. Then finally, model optimization. So if you want to optionally perform feature selection by examining the coefficients of the elastic net model and identifying the most important feature. So let's wrap this up by looking at the code. So now it's time to make the projection. Let me execute and let's see. So these are the important features which were selected by the elastic net, and these are the coefficients. You see that bedroom coefficient, square footage, age of house, bathrooms, garage capacity, overall condition, location, rural, location, suburban, location, urban. And the mean squared error is this is what we got. Okay. So then so you can see the make predictions on the testing data. So ypred we got. After that, you just take the ypred and then ytest basically to calculate the mean squared error. So mean squared error class object has been instantiated, and then respective arguments was given y underscore test, y underscore pred. So finally we can print the mean squared errors. The mean squared error that we got is this much, and now what we're going to do is we're going to compare the mean square error of ridge, mean square error of lasso, mean square error of elastic net, and let's see what is the output. So mean square error ridge and lasso we have seen. Okay, that's in our previous example. What we found was mean squared error lasso is higher than compared to ridge. So ridge was performing better in this condition. You see that? Because this one is the difference between lasso and ridge was positive, so MSE of lasso is higher than this that you can see here, 432 ridge, and this is 445. Same thing applies here. Mean square error of ridge is lesser than mean square error of elastic, and mean square error of lasso even also lesser than the mean square error of elastic net. But overall, when you compare MSE elastic, MSE ridge, ridge wins. MSE elastic, MSE lasso, lasso wins. MSE ridge versus MSE lasso, lasso wins. Sorry, ridge wins. So finally, the winner is MSE ridge. But the other important aspect is applicability. So where it will be applied, that is also the most important aspect. So with this, we have covered up all three feature selection algorithms which are of embedded type.